Welcome to the deep dive. Today we're really getting into something cool, where magnetism meets superconductivity, specifically looking at quantum technologies.
Yeah, it's a fascinating area. And our source today is a presentation from the USC Discover Expedition Seminar Series.
Oh, right, the one hosted at the University of Rochester.
That's the one. It's funded by the NSF, which is great because it helps make this kind of, cutting edge stuff accessible.
Accessible to everyone, yeah. Even like high school students or grad students thinking about jumping into this field, you might find your next big thing right here.
Exactly. So our mission really is to explore how researchers are trying to leverage these things called magnetic Josephson junctions.
Magnetic Josephson Junctions. Okay, let's pause there. A regular Josephson Junction, that's
Right.
two superconductors.
Two superconductors separated by a really, really thin insulating barrier.
And superconductors, that's the zero resistance thing. But the junction lets Cooper pairs the electron pairs tunnel through.
Precisely. They quantum mechanically tunnel across a barrier. It's already pretty wild stuff.
Okay, so the twist is adding magnetism. How does that change the game?
That's the core question. And the work we're looking at involves Francesco Tafuri and a whole network of collaborators.
Like CNR in Italy?
Yep, CNR, Quantware, CQC, SICK, also theoretical folks, Alexandra Bruno from Quant. There's significant backing, too, like the Italian National Quantum Science and Technology Institute, the NQSTI project.
So a lot of brain power focused on this. What happens when you actually put a ferromagnetic layer in the junction?
Okay, so that's your magnetic Josephson junction. You essentially sandwich a thin ferromagnetic layer, like think iron or nickel, between the superconductors.
Instead of just the insulator or maybe alongside it.
It could be SFS, so superconductor, ferromagnet superconductor, or sometimes more complex structures. But yeah, that magnetic layer is the key.
And how is that different from, say, putting a normal non-magnetic metal there? You get that proximity effect, right? Where the superconductivity kind of leaks in and dies off.
You do get a proximity effect, yes.
Yeah.
But it's different with a ferromagnet. Because of the strong internal magnetic field, the exchange energy in the ferromagnet, it actually makes the superconducting order parameter, you can think of that as the strength of the superconductivity, it makes it oscillate as it goes through the ferromagnet.
Oscillate, not just decay.
Exactly. It goes up and down. And this oscillation means the phase difference between the two superconductors across the junction can end up being either zero, like in a normal junction, or pi.
Pi, like 180 degrees out of phase.
Precisely. So you get these two distinct states, zero or pi, which you can potentially control.
Okay, zero or pi states. That sounds useful. How do we know this actually happens? Was there early evidence?
Oh, yeah. Back around 2001 to 2006, there were some really important experiments.
What did they show?
They looked at the critical current, the max current the junction can handle while superconducting, and they varied things like temperature and the thickness of the ferromagnetic layer. And they saw these clear dips or nodes in the critical current at specific thicknesses and temperatures. They used materials like cobalt, permalloy, nickel.
Permalloy, that's nickel iron, right?
Yep. And those dips were strong evidence for that oscillating order parameter and the existence of these pi junctions.
Okay, that makes sense. Now, you also mentioned something about engineering the interface and spin triplet superconductivity. That sounds even more exotic.
Right, so this gets a bit deeper. If you carefully control the boundary between the superconductor and the ferromagnet, maybe adding super thin normal metal layers, for instance, you can influence how the electron spins interact. Normally in superconductors, electrons pair up with opposite spins. It's called singlet pairing. But under the right conditions near the ferromagnet, you might encourage pairs where the electrons have the same spin. That's spin triplet pairing.
And why is that interesting?
Because these triplet pairs aren't as easily broken up by the ferromagnet's magnetic field, so superconducting correlations could potentially survive much deeper into the ferromagnet than you'd expect. Longer range effects.
Wow. Okay. So originally people were thinking about using these magnetic junctions for spintronics, like faster electronics?
Exactly. Superconducting spintronics was the initial big draw. Things like memory elements, digital logic, phase shifters.
But now the focus has shifted more towards quantum computing.
Definitely. The realization was that the magnetism itself, the magnetization of that layer, gives you a whole new knob to turn, a new degree of freedom to design qubits.
An extra control dial, basically. The presentation mentioned graphene aluminum junctions too, controlled by electrical gates. How does that fit in?
That's a good example of the broader idea of hybrid systems. They're using different materials and electrical control, not magnetic, to manipulate the Josephson energy.
Which is key for the qubit, right?
Yeah, absolutely. The Josephson energy is fundamental. So that work shows people are exploring various ways to control these quantum circuits, even if it's not purely magnetic like the junctions we're focusing on.
Got it. So let's drill down on using these magnetic junctions for qubits. The presentation talked about a ferrotransmon. Okay, first step. What's a transmon?
Right. A transmon is probably the most common type of superconducting qubit used today. Its big advantage is that it's designed to be much less sensitive to charge noise.
Charge noise,
Yeah.
like random electrical fluctuations messing things up.
Exactly. Transmons have a large ratio of Josephson energy to charging energy, which kind of smooths things out and makes the qubit states more stable. Robust.
And how does that help you actually use it as a qubit, the energy levels?
Well, the energy levels aren't perfectly evenly spaced. There's a slight difference in energy between the ground state, 0, and the first excited state, L1, compared to the energy needed to get to the second excited state.
A slight unharmonicity.
Precisely. That little bit of nonlinearity is crucial. It means you can use microwaves of a specific frequency to drive transitions just between the 0 and 1 states without accidentally exciting the qubit higher up. It gives you control.
Okay. And standard transmons often use a suite loop, right? Two
Yeah.
junctions.
Yeah, often they do. A squeed is a superconducting loop with 2 Josephson junctions. You can apply a tiny magnetic flux through that loop, and that lets you precisely tune the total Josephson energy of the squeed alert, and therefore tune the qubit's frequency. It's a standard control method.
So the ferrotransmon idea is you swap out those standard junctions.
You got it. Replace one or both of the junctions in that squeed loop with a magnetic Josephson junction. Could be SFS or that SISF structure they studied.
Superconductor, insulator, superconductor, ferromagnet, superconductor. Quite a mouthful.
It is. But the core idea is simple. Use the magnetism inside the junction as a new way to control the qubit, maybe offering advantages over just using external magnetic flux.
Okay, that's a neat idea. So what did the experiments actually show when they built these things? They use niobium and permalloy.
They did in those SISFS structures.
Yep.
A key finding was how important the thickness of that thin niobium layer between the insulator and the permalloy was.
How so?
They found that if they made it just right, about 3 times the superconducting coherence length, which is a characteristic length scale,
Okay.
the junction behaved a lot like a really good, high-quality, normal SAS junction. Good characteristics, high ICN product, a quality factor. But crucially, it was still sensitive to the magnetic field because of the permalloy.
So good quality and magnetically tunable.
Kind of the best of both worlds, yeah. And they saw direct magnetic effects, like a splitting in the Josephson current peaks when they applied a magnetic field.
Splitting, mainly.
Meaning the peak current occurred at 2 different field values, depending on the magnetization state of the permalloy. It showed the magnetism was directly influencing the quantum tunneling.
And you mentioned memory potential.
Yeah, that splitting, that B stability based on the magnet state, it suggests you could potentially store a bit of classical information right there in the junction itself. A qubit with memory.
Interesting. But then there's that weird temperature thing, right?
Ah, yes. That was puzzling. They saw this nice splitting effect at around 4.2 Kelvin.
Liquid helium temperature, still very cold.
Very cold, but relatively warm for these qubits. But when they went really cold, down to 10 millikelvin, the splitting basically vanished.
It went away at colder temperatures. That seems backwards.
It does. You'd think magnetic effects would get stronger, clearer, when it's colder and there's less thermal noise.
So what was the explanation? They mentioned an inverse proximity effect.
Exactly. The theory suggests that the ferromagnet doesn't just affect the superconductor. The superconductor can also affect the ferromagnet right at the interface.
Ow.
It can actually induce a small magnetization in the superconductor right next to the boundary. And this induced magnetization points in the opposite direction to the ferromagnet's main magnetization.
So the superconductor kind of pushes back magnetically.
In a sense, yeah, over a very short range, the coherence length again. And this opposing magnetization can create an effective magnetic flux that works against the flux from the ferromagnet itself.
Okay.
The theory involves a parameter, gamma. At very low temperatures, like 10 milK, gamma gets close to 1, meaning this induced effect almost perfectly cancels out the ferromagnet's effect on the Josephson current. No splitting.
Cancellation at higher temps.
At higher temps, like 4.2 K, gamma deviates from 1. The cancellation isn't perfect, and you see the splitting. They also saw some broadening of the current peaks, which theory also predicted for these SISF junctions.
Wow, that's pretty subtle physics playing out there. Okay, so niobium showed this complex behavior. What about the newer aluminum experiments? Are they getting closer to a working ferrotransmon?
It looks like it. The results with aluminum junctions, specifically oxal permalloy al, seemed very promising.
What did they find?
They got high-quality junctions. And importantly, they did see clear splitting of the critical current, even down at 10 millikelvin.
So they overcame that low temperature vanishing act.
It seems so, at least in this aluminum system. And crucially, the magnetic fields needed to see this splitting were much smaller, around 1 millitesla.
That's way more practical for putting on a chip than needing huge magnets, right?
Much more practical, yeah.
Yeah.
And they measured the Josephson
For transponds?
It was. They found values like 40 to 90 microelectron volts, which is right in the typical range needed for transbond qubits. So it looks compatible.
Okay, but how do you control the magnetism of just one tiny junction on a chip with potentially many qubits?
Good question. They've actually developed and tested a 3D microcoil right on the chip.
A tiny integrated electromagnet.
Basically, yeah. It allows them to apply a very localized magnetic field just to the junction they want to control, without messing up its neighbors.
That's clever engineering. What else are they working on? Anything about tweaking the magnet itself?
They mentioned doping the permalloy, mixing in a little bit of niobium,
Why do that?
to fine-tune its magnetic properties. Things like the saturation field, how strong a field you need to fully magnetize it, and the coercive field, how easily it flips its magnetization. Optimizing those could be key for device performance.
And are they seeing progress there?
Yeah, they showed controllable magnetic hysteresis loops, which is what you expect and need from a controllable magnetic element. So all these pieces, the good junctions, the control low T, the right energy scales, the local field control, the material tuning,
It sounds like they're really putting the building blocks together.
it really does.
Yeah.
The presentation concluded that these results are significant steps towards actually building and testing the first ferrotransbond qubits. Prototypes are apparently under development now.
That's fantastic progress. It really highlights the potential here using magnetism to add this whole new control layer to quantum computing.
Absolutely. And it's worth remembering, like you said earlier, this research came out of that USE Discover Expedition series at Rochester with NSF support. It's about pushing boundaries, but also making the science accessible.
Yeah, accessible to everyone, including students maybe listening now and thinking about their future. This shows what's possible, the kind of collaborative, exciting work happening. The presenter even offered to answer questions, which is great for fostering that next generation.
Definitely. That openness is vital.
So as we wrap up this deep dive, here's something to think about. We've talked about how magnetic Josephson junctions could improve current qubits, but could they enable totally new ways of doing quantum information processing? What other quantum tricks might be hidden at this, fascinating intersection of superconductors and magnets? Something to ponder. Thanks for joining us on the deep dive.